Applications. The evaluation theorem says that if f is continuous on a closed interval from a to b, then we can say that this integral going from a to b of this function is equal to f of b minus f of a, where f is any antiderivative of the function f. Okay, so this means that f prime is equal to lowercase f, so the equation can be written as the following. We can say that f prime of f is going to equal then f of b minus f of a. Now, we know that f prime of x represents the rate of change of y is equal to f of x with respect to x, and f of b minus f of a is the change in y when x changes from a to b. Note that y could, for instance, increase, then decrease, and then increase again, although y might change in both directions. F of b minus f of a represents the net change in y. So we can reformulate the evaluation theorem in words as the follows. The net change theorem. The integral of the rate of change is the net change, which is from a to b of f prime of x dx is equal to f of b minus f of a. Now this principle can be applied to all of the rates of change in the natural and social sciences that we discussed in section 3.8. Here are a few instances of this idea. If v of t is the volume of water in a reservoir at time t, then its derivative v prime of t is the rate of which water flows into the reservoir at time t. So if we go from t1 to t2 of f v prime of t dt, that's going to equal v of t2 minus v of t1 is the change in the amount of water in the reservoir between time 1 and time 2. Now, if we have these brackets here of C of t is the concentration of the product of a chemical reaction at time t, then the rate of change is the derivative. So therefore we can rewrite this now as, again, going from t1 to t2, okay, and it's the change in the concentration of C from t1 to t2. Now if the mass of a rod measured from the left end to the point x is m of x, and then the linear density is rho of x, which is equal to m prime of x, so we would get the following. From a to b, okay, the linear density function dx is equal to m of b minus m of a. This is the mass of the segment of the rod that lies between x is equal to a and x is equal to b. Now, if the rate of growth of a population is dn over dt, then we can say that from t1 to t2 of dn over dt is equal to n of t2 minus n of t1. This is the net change in population during the time period from t1 to t2. The population increases when births happen and decreases when deaths occur. The net change takes into account both births and deaths. Number 5, if C of x is the cost of producing x units of a commodity, then the marginal cost is the derivative. So we can say that from the integral of x1 to x2 of C prime of x dx is equal to C of x2 minus C of x1, and that is the increase in cost when the production is increased from x1 units to x2 units. Number 6, if an object moves along a straight line with position function s of t, then its velocity is v of t, which is equal to s prime of t. So we saw this definition before, where the velocity of t dt going from t1 to t2 is going to equal to s of t2 minus s of t1. This is the net change of position or displacement of the particle during the time period from t1 to t2. In section 5.1, we guessed that this was true for the case where the object moves in the positive direction, but now we have proved that it is always true. Number 7, if we want to calculate the distance the object travels during the time interval, we have to consider the intervals for when v of t is greater than or equal to 0, meaning the particle moves to the right, and also the intervals when v of t is less than or equal to 0, when the particle moves to the left. In both cases, the distance is computed by integrating the absolute value of the velocity function, which is the speed. Therefore, from definition 3, if we take the integral of the absolute value of the velocity function dt from t1 to t2, it's equal to the total distance traveled. So if you take a look at the figure below, it shows how both displacement and distance travel can be interpreted in terms of areas under a velocity curve. So starting at t1, we have the function, okay, that's going to the right. There's area 1 of the curve. And then now we have area 2, which is the negative. And then back up, we have the area of 3 going to t2. So the displacement is the integral from t1 to d2 of vt dt, which is a1 minus a2 plus a3. Now the distance, okay, is the absolute value. So if we want to know what is the total distance, then that means we're taking the absolute value, which means we're taking area 1 plus area 2 plus area 3. Now for the last one, A, the acceleration of an object is a of t, which is equal to the v prime of t. So the integral of at dt from t1 to t2 is equal to v of t2 minus v of t1. And that is the change in velocity from t1 to time t2.